Good morning students. We are going to discuss about the course CS8603 Distributed Systems, and I am Meenakshi, Assistant Professor, Computer Science Department, working in Rohini College of Engineering and Technology. Last class we have discussed about Lemport algorithm, Rickard-Agarwala algorithm, etc. So this class we are going to discuss about another one, distributed mutual exclusion algorithm, that is named as Suzuki Kasami Broadcast algorithm. These are the objectives of this presentation. It is one of the distributed mutual exclusion algorithm, and we are going to discuss about the Suzuki Kasami Broadcast algorithm advantages and disadvantages. Suzuki Kasami Broadcast algorithm is a token based algorithm, whereas the Lemport algorithm and the Rickard-Agarwala algorithm are not a token based algorithm, they are permission based algorithm, but this one is a token based algorithm. This is a modification of Rickard-Agarwala algorithm. The Rickard-Agarwala algorithm used two messages, request and reply messages. So it is the modification of Rickard-Agarwala algorithm. What is the difference between token based algorithm and non-token based algorithm means, in the token based algorithm, if the site is having the unique token means it is allowed to enter the critical section. Whereas in the non-token based algorithm, we are using the timestamp to order the critical section request. But here the tokens are used, and moreover the sequence number is used in token based algorithm. Each request for the critical section contains the sequence number. This sequence number is used to differentiate the old request and the current request. Again, like the other algorithms, here also we need 3 steps: requesting the critical section, executing the critical section, and releasing the critical section. So the first step is entering the critical section. For example, if the site SI wants to enter the critical section, if it does not have the unique token, what it needs to do? So if it is having the token, then no problem, immediately it can enter into the critical section. But if it is not having the token, then what it needs to do means it has to increment its sequence number, that is Rn I of I. After incrementing the sequence number, it sends the request along with the sequence number to all the other sites in order to request the token. So the token may be held by some other site, so it sends a request for that token. So what is Sn? It is nothing but the updated value of Rn I of I, that is the I sequence number. When the other site Sj receives the critical section request message from the site Si, it sets Rn j of I to the maximum of Rn j of I and Sn of I. Okay, that is, it compares its sequence number and the received sequence number. So which one is minimum? Okay, that is taken. Which one is maximum? So that is taken, and it sets Rn j of I to that maximum value. After updating Rn j of I, Sj sends the token to Si if it has the token, and it sets Rn j of I equal to Ln I of plus 1. So what is Ln of I means the last executed number. Okay, so once again I am explaining the concept. So the site Si wants to enter the critical section. It is not having the token. So first it increments its sequence number and it sends the request to all the other sites. In the request message, it has included the sequence number. So what is sequence number? It is nothing but Rn I of I. When the other site receives that request message, it compares its sequence number and the I sequence number. So which one is maximum? that is taken and it is set to R and J of I. If the site Sj has the token, immediately it sends the token to Si and it updates R and J of I equal to ln of I plus 1, that is the last executed number plus 1. So to execute the critical section, Si needs the token. Once the token is obtained by the site Si, immediately it can enter the critical section. To release the critical section, that is Si executed its process, and after executing the critical section, Si releases the critical section and it has to update the following things. That is, it sets ln of I equal to Rn I of I to indicate that its critical section request has been executed. Ln of I, don't forget, it is the last executed sequence number. For every site Sj whose ID is not present in the token queue, it appends its ID to the queue. If Rn J of j is equal to ln of j plus 1 to indicate that Sj has an outstanding request. That is, Si completed its request and it checks whether Sj is having an outstanding request or not. So how it checks the outstanding request? The condition is Rn J of j is equal to ln of j plus 1. After above the updation, if the queue is non-empty, it pops a site ID from the queue and it sends the token to the site indicated by popped ID. That is, which site is top at the queue, it is served first. If the queue is empty, it keeps the token with itself. Okay, once again, Si completed its critical section. So what it needs to do? It sets the last executed number to its sequence number and it checks whether any outstanding request is pending or not. So how it checks? It is checking in the queue. And what is the condition? Rn J of j is equal to last executed number of j plus 1. So if any outstanding request is present in the queue, it is giving the token to that process. Otherwise, it keeps the token. So the message complexity of this algorithm is, this algorithm requires 0 messages if the site is already having the token. If it is not having the token, totally n messages we need. That is n minus 1 request messages and 1 reply message. The drawbacks of this algorithm is, it is a non-symmetric algorithm. That is, if the site don't want to enter the critical section, so it may retain the token even if it is not interested to enter the critical section. The site is not at all interested to enter the critical section, still it retains the token. It is the drawback of this algorithm. The performance of this algorithm is, the synchronization delay is 0 if the token is held by the requesting site. If the requesting site does not hold the ideal token, as usual, the maximum synchronization delay is equal to the maximum message transmission time. So that is, it requires totally n messages per critical section request. So with this, we have concluded Suzuki Kasami Broadcast algorithm. Thank you.